In this video, we discuss section 44, antiderivatives. First, we have a definition that is same as the definition in the real analysis. Antiderivative of small f of z is a function capital F of z. This is what we call the antiderivative of small f of z. If this capital F satisfies the condition that f dash z is equal to small f of z. So if the small f of z is a derivative of the capital F of z, then we can say that this capital F of z is the antiderivative of small f. Now we have a remark on antiderivative. Suppose this f of z has two antiderivatives, say capital F of z and capital G of z. That means if these are two antiderivatives of the same function small f of z, then we will have capital F dash z as well as this capital G dash z will be equal to small f of z by definition. So which shows that the difference between these two, capital F dash of z minus capital G dash of z, will be 0, as the function, the derivatives are this same as this small f of z. So this implies d by dz of capital F dash minus capital G dash, sorry, capital F minus G, this is capital F minus G, is 0. Okay, so which shows that f of z minus G of z, the derivative of this function is 0, means this function is a constant. So if we have any two arbitrary antiderivatives for small f of z, then that is that can be connected through this equation. That means that is obtained for any antiderivative of once you are given an antiderivative of capital F of z for the small f of z, then any arbitrary antiderivative of this small f of z, say this G of z, this is an arbitrary antiderivative, then that can be obtained using this f of z. That means the only difference between these two are the difference of this c. Okay, so that means an antiderivative of a given function f of z is unique up to an additive constant, or except for an additive constant. That means if you have any antiderivative, then that can be obtained by adding or subtracting a constant with this capital F of z. So if this small f of z is a function, then if there exists at least one antiderivative for the small f of z, then all the antiderivatives of small f of z takes the form capital F of z plus c. So this will be the arbitrary form of, or general form of antiderivative of the small f of z. That is, we have a remark, an antiderivative of a given function small f of z is unique except for an additive constant, say some c. Now we have a theorem. Suppose that a function f of z is continuous on a domain D if any one of the following statements is true, then so are the others. That means there will be three statements A, B, C, in which, or we can say that those three statements are equivalent. This is the first statement: f of z has an antiderivative, a capital F of z, throughout D. That means this theorem can be considered as the characterization of the existence of antiderivative. So if A holds, then the other two, B and C, holds. This is the second statement, statement B. The integrals of, that means if A holds, f of z has a antiderivative capital F of z throughout D, then the integrals of small f of z along contours lying entirely in D and extending from any fixed point z1 to a fixed point z2 all have the same value. That means the integrals from z1 to z2, suppose we have a domain, and suppose we have a domain like this, and if there are 2 points z1 and z2, and if we have a contour joining these two, then the value of the integral, the value of the integral of f of z from z1 to z2 along this contour will be this capital F of z2 minus capital F of z1. So this capital F is nothing but the antiderivative what we have assured here in A. There is an antiderivative. If antiderivative exists, then this holds, and for the equivalency we will get the other the reverse implication as well. This is the third statement. The integral of f of z around closed contours lying entirely in D all have the value 0. That means we have already if we assume this B f of z2 minus f of z1 as the value of this integral, then if you consider any closed contour, that means if you have a domain like this, and suppose we have a domain like this, and we have a contour starting from suppose this is z1, and this is a closed one, and z2 coincides with z1. In this case, we know that f of z2 minus f of z1 will be 0, okay, because of B. So C says that from B we can easily prove C, the integrals of f of z around closed contours lying entirely in D, as its value is f of z2 minus f of z1, and for a closed contour z2 and z1 are the same, then these two values will be the same, and we will get the value as 0. So for all integral values will be 0 along any closed contour in this case. So antiderivative exists means the integral exists, and integral will be 0 for closed contours which entirely lying in D. The proof of this theorem is given in section 45. Fortunately or unfortunately, that section 45 is not included in our syllabus, so we are not going to elaborate on the proof of this theorem, and you are not supposed to study the proof of this theorem as well. So we move on to do some illustrative problems of the regarding this theorem. So first we have a example 1. For example 1, we have a function f of z equal to z square. We know this function has antiderivative, say capital F of z, which is equal to z cube divided by 3. Then we can easily evaluate the integral 0 to 1 plus I along any contour z square dz equal to z cube divided by 3, because the value can be obtained using this argument, using the antiderivative from 0 to 1 plus I. This is nothing but the fundamental theorem of calculus what we have learned in your 5th semester in real analysis. So this is in fact the value is 1 by 3 times, first of all we have to put 1 plus I times whole power 3 minus 0, so the value will be 2 by 3 times minus 1 plus I. So when you evaluate this, you will get this one. So this is the first example, and if you have another function like f of z equal to 1 by z square, we know that this function is analytic except for z equal to 0, because the denominator contains z. So at z equal to 0, this function has singularity, or it is not analytic at z equal to 0. So if we are considering any closed contour which suppose the domain of this function can be taken as this, removing the origin from this complex plane, say C minus singletons at 0. So this is the domain of this function, and if you consider any closed contour which fully contained in this, if you consider any closed contour is fully contained in this, then this can also be expressed as or represented as mod z greater than 0. Mod z equal to 0 represents the origin, so mod z greater than 0 gives this one. So if you consider this function, and if you take any integral of this function over any c, this dz by z square. So here c is defined as z equal to 2 times e to the power I theta. Okay, so this theta lies starting from minus pi to pi. Then so this is the integral of this f of z. Even though it is not analytic at z equal to 0, we can consider the integral of this, because our domain is in our domain this function is analytic. Okay, so the value of this is always 0. As this this is a closed contour like this, then the value of this integral depends only on the antiderivatives or endpoints. So this can be written as, if this is closed contour, then the value integral over c dz by ez square can be written as minus 1 by ez, starting from z equal to 0, z equal to 2, right, z equal to 2 to z equal to 2 itself, because the c has the starting point as 2 and the terminal point as also 2. So this value will be 0. So this shows that the integral value of this is always 0. And there are two more problems have been discussed in this session as well, so please go through it. In the next class we will discuss section 46.